afternoon, everyone. Thank you. Welcome to today's Clean Lakes 101 Science Cafe. I'm Dana Fulton, meteorologist and anchor at WKOW. Our station is very proud to be the media partner for these events. I've been hanging out now for 3 years, I think, coming to MC the 101s, and I love every single one of this. It's such a wonderful education and connection experience. I'd like to welcome everyone to the East Side Club. Hopefully you found parking, because it's really busy out there today, and everyone hanging out outside too. Who here is part of Clean Lakes Alliance's water quality monitoring program, Lake Forecast? Raise your hands. Thank you. Yes. For those unaware, if your hand is not in the air, here's what we're talking about. Lake Forecast is a citizen science program powered by trained volunteers, those with their hands up. They collect valuable water quality data every summer, and then they share it in real time with the public. We use that sometimes in our newscasts. It's incredibly helpful just to be able to talk about what people are experiencing, what they're actually seeing out of the water, out at our beaches. Among the many parameters that the monitors are collecting information on, such as the presence of algal blooms and the clarity of the water, it's water temperature data. Today's talk focuses on rising water temperatures, but also highlights why data collection is crucial to better understanding our lakes. Titled, Monitoring a Century of Warming Lakes in Wisconsin. Yes, 100 years. Today's talk will discuss the importance of data collection and the long-term trends that these data sets reveal. Our presenter will also share insights on the impacts of warming temperatures and what it has on our lake ecosystems. As usual, we will have time for a Q&A session at the end. I did hear from Dick earlier, though. He might be talking all the way up until 5 o'clock. He's got a lot to share with you guys. So we're going to try to get to as many questions as possible at the end. And as usual, if we don't get to those questions, we can always email Clean Lakes Alliance. We'll get those answers to you as quickly as possible. I want to throw out another thank you to our Clean Lakes 101 sponsors. Presenting sponsor, National Guardian Life Insurance Company. Hosting sponsor, the East Side Club. Supporting sponsors, Johnson Financial Group, Alliant Energy, and Perkins Coie. Production partners, the UW-Nelson Institute for Environmental Studies and the UW Extension, and the media partner, WKOW. Now, before we get started, I do want to let everybody know, as many of you have already found out, the bar is open. You can go back there and get a drink. And for those of you who received a pink ticket when you walked in the door, we want to thank you for being a 2026 friend of Clean Lakes Alliance. When you become a friend, we're all already friends, but this is like a bonus kind of friendship, you get a free Bell's Two-Hearted IPA at every Clean Lakes 101 this year. Pretty good deal. So you can become a friend today. You can do it online, or you can go over to talk to Ryan or Olivia at the blue table at the front. At the check-in table, they can help you if you would like to become one of our closer friends. Your support help fuels programs and partnerships that continue to improve water quality, lake access, and community engagement throughout the watershed. So let's go back to today's talk, not just beer. Here to share more information about warming lake temperatures, we have Dr. Dick Lathrop. Dick has been studying Greater Madison's lakes for more than 50 years. He spent 33 years at the Wisconsin DNR as a research limnologist, earning his PhD in oceanography and limnology at the UW Center for Limnology later in his career. Dick has held an honorary fellowship position at the Center for Limnology, where he continues to work on their North Temperate Lakes long-term ecological research project. He has also been a volunteer science advisor to Clean Lakes Alliance on their Yahara Lakes water quality initiatives, plans, reports since Clean Lakes Alliance's inception in 2010. So thank you for 16 years of helping out. Here to share more about the importance of data collection and the impact of our warming lake temperatures, please join me in welcoming Dr. Dick Lathrop.
Thank you very much. It's really a pleasure to be here. I know many of you people out there, I've encountered you at various meetings and whatever, and hopefully this talk will be stimulating to you.
Keep the mic up.
Can you put the mic closer to your mouth?
Okay, is this better?
Yeah.
All right, sorry. What I said before doesn't really matter. I'm trying to get, oh yeah. Well, Karen didn't like my title, it's too sciencey, so Karen made a shorter one for you. But this is what it's really about. Lake Mendota and Trout Lake in northern Wisconsin, Trout Lake, are Wisconsin's sentinels of water temperature changes. Many people are co-authors or co-contributors on this project. I want to particularly mention Dale Robertson. He and I are good friends, been for 40 years. He collected, or he transcribed a lot of the data that were in the archives of the UW. So we have a longer record thanks to Dale's help. Lake Mendota is a fairly large, deep lake, 25 meters. It thermally stratifies in summer. Trout Lake is also fairly large and a lot deeper. 43 latitude for Mendota and Trout 46. There are not 397 slides here, but I do have a lot of graphs. And I'm a data guy, so I'm going to try to walk you through every graph so you understand what's in it and what are the important points. Clean Lakes Alliance, first thing they said to me, well, we want you to give us a whole lecture on why we care. Well, I got one slide, and I think the first point is really well taken. The thermal tolerances of cool water aquatic organisms are exceeded, causing altered lake food webs and loss of biodiversity. That's when the surface water temperatures really increase. Epilimneon is the upper mixed zone waters. I use that term a lot. It's a lot easier just to say epilimneon than surface mixed zone waters. Of that same issue, warm water species are favored. So walleye are more of a cool water fish. They're not as favored as largemouth bass are. So in northern Wisconsin, there's a big issue about walleye declining where largemouth bass are increasing. Carp, of course, we've been working a lot of carp down here, and some of you know that I've been a real advocate for getting the carp out of lakes or decreasing their populations, like in Lake Wingra and other places. And many aquatic plant species, too numerous to mention, I wouldn't even know half of them, are really cool water species left over from glacial relics and whatever, so they are definitely affected. Increased duration of thermal stratification. As the lakes warm in spring, they thermally stratify if they're deep, and that will extend later into the fall as the water temperatures are still warm. And in the bottom of our eutrophic lakes, like the Madison lakes, hypolimnetic anoxia, no oxygen, is extended, even in moderately fertile lakes, thus eliminating refugia in late summer for cold water species. So here's an example of Cisco die-off in Lake Mendota in 1987. They're a cold water species, and the lake got so warm that summer with no oxygen in the bottom, and there was a massive die-off. Trout, for example, are also another cold water species where they need cold water, but they need oxygen in it. So the refugia could be lost. Extended anoxia also promotes internal recycling of phosphorus, leading to enhanced eutrophication. Nutrients build up in the bottom, they come up into the water, they come up farther into the water, and as the anoxia is extended, that encourages recycling, and so that's a problem that in Europe they really talk about this internal lake eutrophication. But the biggest one is increased cyanobacteria densities and exposure risk to toxins. Limnology, the common name, but they're really cyanobacteria. Cyano meaning they have pigments that they photosynthesize. They can produce toxins that are deadly. Well, kidney and liver toxins are called hepatotoxins, and the antitoxins that are the respiratory toxins. And actually, this is a slide I remembered that I had put together many years ago. The first death in the United States was recorded in a golf course pond here in Madison on the south side, and that was due to anatoxins. So these toxins are really a serious problem, and they're coming from blue green algae, cyanobacteria, and warmer water that extends longer in the season, there's more exposure risk. Well, everybody here probably has some sense of climate change. Maybe you've seen graphs like this. This is an annual air temperature trend in the United States going way back to 1880. I updated it from 2025. And your eye immediately goes to the red line, which is the smoothing curve. But notice all the variability year to year in this. And it's some of these warm periods back here in the 20s and 30s and some of the Dust Bowl years. And certainly we're seeing some really warm temperatures here annually in the United States. This one is 1921. We'll be talking about that year some. Mary is a seat up here in the front, Mary. My friend Mary and her husband Dennis, I don't know if Dennis here, but they are sampling for me on a nitrogen study up in Cherokee Marsh. So a lot of variability, but this is the annual air temperature, winter, spring, summer, fall, for the hot and cold United States. But if you look at the Madison air temperatures for summer, and meteorological summer, these are what the climate scientists call meteorological summer, is the months of June, July, August. This is the average daily temperature, so it's not the maximum during the day or the minimum at night. But if you look at this long-term record that Dale Robertson has helped put together, because the station has moved, and when you move a station or you collect the temperatures at a different time of the day, you have to kind of standardize it to get a really good record of for the long term. But these are the meteorological summer data for Madison going back to 1890 through 2025. You see a lot of variability in the record year to year. Each one of these is the yearly value. Here's the 1921 value. 1995, I remember that summer a friend from Germany came over, and his wife, he was here on a year-long sabbatical, and his wife came over in that summer, and I thought they were going to die. You could cook eggs on the sidewalk. It was so hot. And it actually turns out to be, in this record, the warmest summer that we ever had in the record. Here's 2012, that was a severe drought we had, very hot. You remember that? We've also had some cool years, and 2009 are particularly notable. And here's another one in 1992. I'm lining it up, either this one or this one, but one of the really cold summers. Well, here's part of our long-term record. Bruce Juday, he was the president of the university, but he also was really interested in limnology. He's considered the father of North American limnology. It gives the notable that Wisconsin has been considered the start of limnology in North America. If you go to Europe, they have their own places. They've studied it for a long time. So I don't quite have the hubris to say that we are the longest record of limnology, but certainly in North America. And it's the first place that limnology was taught at this university anywhere. Chancey Juday, the younger guy to his side, he continued and helped George on so many samplings through his career from the early 1900s all the way up through the early 1940s. So a lot of sampling on Lake Mendota. The record goes back to 1894. But there are a few periods of gaps, and you'll see that in a second. And after that period, UW grad students, Robert Rogowski here in this photo was out in the 50s doing all kinds of lake temperature stuff. Here's myself a couple times. Dale Robertson was working a lot for his PhD thesis. And then the LTR, the Long-Term Ecological Research Project that Dana mentioned. The North Temperate Lake site is here in Wisconsin. There are like 26 other sites or so around the country, including in Alaska, Puerto Rico, Antarctica, They all do different biomes or different types of places like prairies, like forests, like estuaries. But the North Temperate Lake site here is in Madison, and we're really fortunate that that has kept this long-term record going. At Trout Lake, they were sampling way back in the early 1900s, not so frequently in the very earliest of those years, but then in 1925, the Trout Lake station was built. The first station, it was moved subsequently, but they were up there every summer. So they were having their summer vacations up there, and you'll see that there's been a lack of data here in Madison in the summer while they were up north. And then LTER, I call LTR, the North Temperate Lake site, has been recording water temperatures starting in 1981. And we have some buoys now. Maybe many of you use the Mendota buoy. You can get that online through the Center for Limnology website. That really fills in the record. I've used that record in places where we didn't have the same extent of normal sampling that we do from a boat. That was particularly evident during the years of COVID. So we're relying more on the buoy data. And here are the three people that have been running the long-term ecological research project. Steve Carpenter on the left, Emily Stanley, the one that's currently running it. But John Magnuson, I really want to point out, many of you know John. John was the one that went to Washington with a few other scientists and really advocated to National Science Foundation, we need to be studying lakes in the long term. We can't be just sending grad students out for 2 or 3 years at a time sporadically and get any kind of data that helps us understand the long-term trends. So John here is a good friend of mine. We share an office still down at the university. John right here. So the Trout Lake sampling started in 1981 when he got the project. And we were, the DNR where I was, we were sampling Lake Mendota or the Madison Lakes up through 1994. And then that project segued seamlessly over to the UW. I was in charge of the monitoring at the time, but then other people have taken over since then. But what I'm calling the LTR era in the data that are coming up from 1981 to the present, but really the sampling, okay, the thing went off. I will shout. I've been known to shout loudly. So, procedures. You have to have a metric that you're measuring. It could be some data point you collect, or you have to do a calculation of other data. So you need a metric that you're comparing the trends over time. You got it back. Okay. Oh, you better sit up there. So we want to compare the results of Mendota and Trout of the LTR era to the longer records that exist for each lake. So the first thing we have to do is calculate a hypsometrically volume-weighted temperature. What the hell is that? Well, that is the volume of a lake in a bowl. So you take the 0 and the 1 meter temperature value, get an average, and it has its own volume at the surface. Then you do the 1 and the 2, get an average, and that volume is slightly less, and so on down. So you get a weighted mean temperature. And with the buoy data, I didn't want to just still use daily data because that would not be consistent with the other longer records. So I would only use it weekly when we didn't have data. And I would take the noon sample because at night it would be cooler, so I thought it would better be using just one sample for that week, and that would be at noon. And then from those data, we would calculate a time-weighted mean monthly temperature. So we did it for May, June, July, August, September, October for Mendota, and the same for Trout, except the Trout Lake is a lot of times still frozen in early May, so I did not calculate a mean monthly temperature for May. And then we also, in earlier analyses that I did with many others, I also calculated the first of the month temperature, and that's provided some other insights that I'll talk about. And finally, I identify each year's maximum recorded temperature. That was a metric that I felt really could tell us some other things, like how hot the lake get that we measured it in a particular summer, as opposed to a longer average. Well, here's a graph that I put together as part of an earlier study that's been published, but I think it really shows how a lake warms, and I wanted to walk you through it in case you're not used to seeing a lot of these profile data. This is in Devil's Lake. That was part of our other study. That's one I'm still sampling frequently. You can see here with the light blue, with the pointer right, these are all end-of-month temperatures. So the profile is starting to warm up, but it hasn't fully gotten its epilimneon established, but it's still warm in a very warm end-of-month May temperature. But the bottom temperature, you can see, the lake is thermally stratified, but it's still colder than it is in the middle of the summer. Then June, pretty much all the same temperature down to 5 meters, and then you get the thermocline or metalimneon in the middle of the epilimneon upper, hypo bottom. Okay, meta is in the middle, but there's a zone between the metalimneon and the hypolimneon is changing as the season goes on. But I'm using 5 meters as the depth range to give us an index or a metric to look at how upper waters are changing. Now here's a July, pretty warm July, kind of like we had back in mid-June, mid-July here this year. The surface waters are quite warm, but this will mix, as soon as it goes at night, it will cool down a little, that'll mix, or you get a cold front come through, that'll mix, and so you get, this could be very variable. If you were to take satellite data, only getting the surface, you're not getting a good stable temperature value for a period of time. You're only getting the surface. So if it's a hot day, it's going to show it's really warm. If it's a cooler day with wind or whatever, the temperature won't be as warm. Then notice as you cool off from end of July to August. As you cool now, that temperature of the surface cools, it becomes more dense and it sinks. So you get convection going on there, and that usually gives you a very stable temperature in the fall cooling period. So here you've got August, it's cooling off, and the thermocline is deepening. The epilimneon, I should say, is deepening. And then here is September. It's still stratified, but you've lost a lot of heat from the end of August to the end of September, but this 0 to 5 meter zone is giving you whatever that temperature is. Well, just recently I was working with the Lake Mendota Association people, and some members are here, and the folks, Friends of Lake Mendota Society, and we went out and sampled in a really hot period. And one of the interesting things, okay, so I took the Mendota buoy data, I wanted to get the exact buoy data at this time, and you can see the surface temperatures in the deeper lake are not as warm as they are in the shallower lakes. So as time goes on through the summer, heat is transmitted and pushed down into the bottom. Oh, I want to go back one thing. I want to make a point here I forgot to really make. So early in the summer, the hypolimneon temperature has not stabilized. But as you go later in the summer, usually by the middle of July through the summer, that temperature hardly ever changes. So if two people are out measuring temperatures with different instruments, you can check to see if the instruments are reading the same, because if you get a hypolimnetic temperature in one instrument that's different than the other person's, then you know there's a problem in the 2 meters. So I use that a lot to tell me if the profiles through the summer, if there have been 2 different groups that we're monitoring, are getting the same data. So back to this one, you can see how warm Kaganza is, Wapisa in between, Kegonsa's shallower, it's a big round lake, and water currents or wave action and wind is stirring that up, and so it's transmitting a lot of heat down into the bottom. So the bottom temperatures are a lot warmer, and it's subject to a lot more mixing. So as the weather starts cooling off, that temperature will decrease here and become more of the similar, and it's easy to mix any nutrients that are building up in the bottom. And on this particular day, I was really surprised that there was hardly any oxygen below 5 meters in these lakes. In fact, at 6 meters to the bottom, they had no oxygen. Nutrients were really building up in there, even though the bottom temperatures were that warm. Any bacterial action is really cooking down there. Well, seasonal temperatures. This is part of the study that I mentioned before. So this is the first of the month data, the medium temperatures, and you can see we've plotted for a whole bunch of lakes going from in Germany and Finland, as well as Mendota plotted here. Mendota and Trout Lake plotted here. You can see that the temperatures are warming rapidly from the 1st of May, 1st of June, up to about the 1st of July, and then they kind of plateau out. And but on an overall trend, this plateau for all these lakes I'm calling limnological summer. So again, meteorological summer is what the climate scientists are talking about for June, July, August, but lakes, limnological summer, I'm calling July, August. And that's a good metric then to calculate the mean temperature of that plateau. It would be right here. Well, there's a lot of coherency between lakes in the south and the lakes in the north. Shared variance, R squared. Correlation coefficient, maybe some of you are familiar with that, that's the square root of this. So July, August is about 0.8, correlation coefficient is 0.9. I mean, a shared variance of 80%, that is really very similar. So when the lake warms up in the south, it's warming up in the north. And for the July mean metric and the August mean metric, those are very high correlation coefficients, or coherency, R squares. And even June and October are statistically significant, but Trout Lake is cooling off faster in the fall than Mendota, and Mendota is warming up faster in the spring than Trout. So that's excuse me, that's why their coherencies are not. I'm gonna have to get some water here. Let's see.
He's got it.
That's why they're coherent. I got it right here. Okay. That's why their coherencies are not as great. Take a second. Sorry about that. So these are the kind of data I'm going to be showing you. They're on for each metric for Lake Mendota. This is the record going back to 1890, in this case 1895, because they started sampling in July or August, I think it was 1894. So one of the first things you see, look at all the variability in each one of these yearly values for that particular metric of May and June. And then I plotted the red line, which is the LTR era record, so you can kind of get a sense how the more recent record would look compared to the longer record. Well, statistically, people might say, well, you got a gap in the data, so this is where a lot of the sampling wasn't done anymore here in the Madison Lakes. Actually, the city was doing the monitoring, and they collected their once a month, and they were collecting temperatures on little note cards. They stored them, and they got thrown out when they moved the lab off of Lake Mendota. So we would have had some data in between here, but unfortunately, those data are lost, but still it's quite a record going back to 1894-95. So of this trend, 0.11 per decade, or you can multiply by 10 per century, so about a degree per century on that trend. In June, Okay, the other thing to note is the p-value. If the p-value is not 0.05 or less, then it's not statistically significant. The trend slope is too flat, and there's too much variability to give you a significant relationship. So the LTR data indicates, even though there's a slight increase in slope, wrong button, slight increase in slope is not even significant. For June, there is an increase in slope that's almost significant. So red here, but the long-term data are much less, but again, close to about a degree per century. Here are the summer data. I should also point out that I plotted everything with the same scale, of this case 10 degrees Celsius, so that you get the variability of it, you get a feel for by how much the black lines go up and down. So the variability back in the spring data are pretty significant, and even in June too. Summer is tightening up a little bit, but notice this one data point here, 1921. That was that 1 year I pointed out on the long-term trends of the national data. It was cooking. It must have been terrible here in Madison in that year, because that's the warmest value we have on record here. And it's also the maximum value here, right there. It was in early July, and in Madison, they must have been cooking here, and yet that's what the water temperature data was telling us. Again, you see the statistics. Now we're starting to see a significant trend in the July mean of the LTR data, but the trend is much steeper than a longer trend that you get from the longer record. And I'm going to summarize this in another way in a minute, but I just want to see the data. But look at the maximum recorded temperatures. The current data, probability of 0.51, is no significant trend in that. It hasn't gotten any warmer. And you go back to the long record, it's been slightly warmer, 0.06 degrees Celsius per decade, and the trend is almost significant, but still a lot of variability. The fall data, though, are really interesting. Both September and October of the LTR record, so we're starting 1981 to the present, last year, a really significant trend upwards of water temperatures. Now, this doesn't mean September is warmer than August. It just means the cooling has been delayed, okay? So I call it delayed cooling effect. But our Septembers are getting warmer as a trend. In other words, it's not cooling off as much as it did in the earlier years. And yet, when you look at the longer record, I'll come back to this point, but I want to show it right here again. We're starting in a cooler period of a bunch of years, and that affects the trend slope. Here's October. It is basically, statistically, there's been no increase in our October temperatures over the long time, but on the short term, we've seen a big increase. So the longer record for Mendota has really helped us discern that. So this data here are the means per period. So I broke the Mendota record out into 4 periods. The early period, 1894 to 1927, when there was a lot of data. And then the 1950 to 1980 period, when there was a lot of students, and I was just starting to sample it myself, but mostly the student data of that period. And then the LTR period, I've broken down into 2 chunks, only because we've seen some increase in the LTR era, 45 years. So if the fat bar, the horizontal fat bar, is the mean of that period of water temperature, and the vertical bar is the confidence limit. So if these are overlap, there's no statistical difference. But if they don't overlap, then these two periods of temperatures are statistically significant, okay? And I'll summarize that in my end, but you can see then, for example, in May, between the student era data, 1950, 1980, that's close to about 11.5 degrees, and that's a little warmer than 12.5. So there was a big jump in temperature in the May period, but then in our more recent LTR era data, there hasn't been any change. June really shows there's no statistical significance difference between these other than the student data and the more recent LTR. These don't overlap, whereas everything else does overlap. Thing went off. Goodness gracious. So September, the only period that September shows any change, these are all the same median temperatures by these three eras. But finally, the most recent LTR data, given the trend slope was going up, shows that in the last 25 years, the LTR, more recent part of it, speaking back, okay, the more recent part of it is significantly different than everything early. October, though, even though there's a difference between these two periods of LTR data, or almost difference there, there's been no change in the longer record going back between even now back to before. So that was the fall data. So now we're going to the summer, and the summer data show no real change in the earlier parts of these three eras. Fat fingers, sorry. No. Yeah, back there. So with the more recent period of 25 years, the temperatures have gotten warmer. So that's about 23.5 going through here, and that's about 24.5. That fits the same thing I found in the trend slope, about a degree over the centuries between this period here and here. So it's gone up about a degree in the last 25 years from everything from before. August, about the same, although this was kind of transition, but this one is definitely warmer than these two periods here, and it's close to a whole degree. The same for the July-August limnological summer metric, as in August. Transition here, not statistically different, but this more recent 25 years is about a degree warmer than the earlier record. Maximum recorded, well, it's gone up slightly as a mean, but they are not statistically different. So we really haven't seen a big change in how warm the lake got as its maximum. So what does this mean? Well, I had plotted this as part of this earlier study, and it really shows the same thing. The frequency distribution. So you go out and you can find a few cold summers in both eras. This would be all the LTR record up through 2017 versus the really early data of the Mendota record. In each set of data, there's a few years that are really cold and really warm, but there are more frequency, more data, higher frequency of summers in this warmer period. And I think we've had warmer years in the last 8 since 2017, so that in essence would build up more red bars on this side and it would shift the distribution. So the point is that the long-term increase in temperatures are due to a higher frequency of recent summers with warm epilimnetic temperatures throughout the summer as an average, and not due to recent summers with new record high lake temperatures. They're not getting any warmer than they have except as an average, and that's because it's staying warmer in August and on into September. We go to Trout Lake. Trout Lake, they didn't have much data collected in the spring other than one sampling where I could calculate a metric for June here. And here's the trend. It's not significant. So much variability, but it does go up slightly. That's June. Here's that steep slope in September, steep slope in October. Remember 1981 to 2025 in Mendota had the same steep slopes. Interestingly, back there in October, one year we had enough data to calculate is just about as warm as it is today. In summer, these are the same data for the July mean. Now they were sampling the summer in the Dust Bowl period of 1925 through 1941, including the Dust Bowl. And the July mean, there really is no statistical difference between the longer record, whereas there is some slight increase in the more recent record. August, the same kind of thing. Slight increase in temperature here. The July-August mean, interestingly, it's all kind of moderated here. It doesn't have some of these warm summers, but the mean is about the same through the period, whereas more recent record shows an increase. In the maximum recorded record, there were summers where it was cooking up in Trout Lake, but they tended to be early. So here's Trout Lake, the maximum recorded. Variability, but the means really hasn't changed, whereas there's been a slight increase in the more shorter record. So summarizing the Trout Lake data in the same way I did with Mendota, in this case I've got 3 periods. I've got the early, but there's no data from June, September, October, so I'm breaking down the LTR period into 2, and you can see that June, there's slight increase in June in the more recent years, but not statistically different, the means. Big change in September, big change in October, just like in Mendota. In the summer, the early years, I'll call it the Dust Bowl era years, of July and now are not any real different, but we are seeing slightly higher temperatures here in more recent. Same with August. That fits with the July-August limnological summer. So August in the last 25 years is higher than it was in the early part of the LTR record and higher during the Dust Bowl period. Maximum recorded, though, between the Dust Bowl era and the more recent LTR really are not different, although it was a cooler here in the earlier part of the LTR record in the 1980s and 1990s. Well, the significance of this, here I plotted back to the October mean data, and you can see in both cases, Mendota and Trout, the LTR record, have gone up a lot. So if you're just starting to sample this lake in 1980-81, and you look at the data and say, wow, it's really increasing. But the longer Mendota record shows it was really an anomaly that occurred in this 1980s period. So I'll read off the slope here, what it is. The large apparent increase in fall temperatures since 1981 was a discontinuity resulting from a cluster of particularly cool falls during the 1980s through the early 90s that in effect pulled the start of the trend slope down like a teeter-totter. So if climate studies have cautioned that the starting date is an important consideration in climate trend analyses, and that analyses of short-term records can produce trends that diverge from the long-term trends because of short-term changes and discontinuities embedded in the longer time series. So it just highlights the importance of how having this longer Mendota record with the gap filled in with what we learned about Trout Lake in the very warm summer of some of the Dust Bowl years. And if even the 45-year record of LTR, we wouldn't have really seen what's been going on. Hypolimnetic temperatures, bottom water. This metric is, I'm using 20 meters depth from middle of July to middle of August. And you only need one sample. If it's a good sample, if you get 2 or 3, they hardly change at all. Sometimes not even 1/10 of a degree. So you can see the variability between years there. Now I put them both, Mendota and Trout, on the same scale. So each have 10 degrees Celsius difference. Mendota's got a lot more variability in its longer record than Trout. Trout's smaller, very much deeper, and Mendota is more subject to wind action, but the hypolimnetic temperatures trends have been going down. Now, a cold summer, Madeline McGee, who's now working for the DNR, she did a PhD thesis here at the university and a lot of modeling on some of these temperatures. And she showed that in the spring, if you have a really warm spring where the lake warms up rapidly and it's not too windy, the bottom temperature will stay cold. It hasn't warmed up, the stratification has developed early. So that would give you, by summer then, a much colder hypolimnetic down at the bottom. Conversely, if it's a cooler spring and you got a lot of wind and that temperature is in the surface waters is being pushed down into the bottom of the lake is warming, and you're going to end up with a much warmer bottom temperature. So remember, the surface temperatures in Mendota averaging about 24 degrees Celsius, sometimes a little warmer than that. But the bottom temperature, if it's up around 15 degrees, that's not very big difference between top and bottom. And you can get a lot more vertical mixing of nutrients coming up from the bottom if the bottom temperatures are that warm. On the other hand, if the bottom temperatures are as cold as, say, 8 degrees Celsius like here, or 9, then the stability of the water column is greater. The density differences of that cold water are going to keep that nutrient more down in the bottom. So it does make a difference. Remember, I was talking about Waubese and Gaganza particularly. That bottom temperature is not that different from the top. You cool the top down a little bit, you're going to get a lot more vertical mixing, bringing nutrients up from the bottom of the lake, which is a lot shallower. Air versus water. I just thought it was really amazing that we could take something as simple as a meteorological summer value, June, July, August, and plot it relative to its water temperature for the limnological summer and get these kinds of relationships. I got to go through this quickly because I'm running out of time. April air is a predictor of the first of the month, in this case, May 1 water temperature. You can see the relationship here. Cold April air, cold first of the month, May 1 water temperature. Warm April air, much warmer. Here's a case where May air and June 1 data. Well, what's interesting is, it really surprised me, and it's surprised the reviewers of this paper, that the May 1 water temperature has no influence to speak of on what the June 1 water temperature is. It's all in the weather that we're having in the few weeks that lead up to that start of the month. So just because it's warm in the first of June doesn't mean that the water temperature, doesn't mean that the July 1 water temperature will be warm. And this holds throughout the whole year on all lakes. So here's the data for October. October mean air, look at the relationship to the start of the November water temperature. If it's warm in the summer, if it's warm in October, it's going to really affect how warm it is by the 1st of November. But yet, again, October 1 water temperature really has no effect on 1st of November 1. So it's all in the weather within a few weeks or less that's affecting what the water temperature is going to be. One other little thing I was interested in is, Trout Lake had some really warm temperatures summers. When does that occur? Well, it tends to occur early in July or mid-July. The warmest temperatures, summers, here in the 25-26 range, only occur in July, they don't occur in August. So there isn't, think about it, Trout Lake, solar angle is highest in July. If it's not too cloudy, dry conditions, there's more solar radiation occurring. By the end of August, my wife and I had a cottage up north, and I can tell you going out in the lake in the end of August wasn't fun because it cooled off. But in July, you get the warmest temperatures. Future work. Summer water temperatures are really coherent to meteorological conditions. Mount Pinatubo exploded erupted, I should say, in the Philippines in 1991 in June, and it went so far up into the stratosphere it went globally. And that really affected the water temperature the next year in Lake Mendota. So both in Mendota and Trout Lake, it's been noted all around the globe. So just an indication, global dimming, wildfires might have an effect. Certainly air temperatures are a big factor, and of course I talked about wind speed, humidity. If the temperatures are not cooling off at night as much, then we're extending the temperature effect later in the summer. So a lot of meteorological effect factors to consider. One last thing I wanted to show is under ice water temperatures. The weather guys put out a thing last winter, I think it was, saying, well, when the lakes reach 4 degrees Celsius, which is their maximum temperature, then they quickly will form ice. I wrote them back. John Magnuson and I published this graph with a bigger thing we were writing, and I told the guys, because all the temperatures I had been monitoring, you go out of Mendota, you got to squeeze the last bit of heat out of that lake down to about 1 degree Celsius before you can get the surface temperatures to cool off enough on a cold night to freeze, because the lake has so much momentum with its water circulation. It's bringing up 2 degrees centigrade Celsius water, is bringing it up. It's preventing it from freezing. So you've got to constantly get rid of all that water, that heat, down to about 1 degree Celsius. That's different than, say, shallow, smaller lakes like Lake Wingo. So I go through the generalizations here. We recorded temperatures using a metric of 0 to 5 meters. Interannual temperature metrics are really variable. A limnological summer represented by July-August temperatures. Mendota's temperatures were generally about 2 degrees warmer than Trout's, but exhibited strong temperatural coherency, especially in summer. Mendota's spring epidemic temperature increased about an average of 1 from the 1980s, but June didn't change much. Epilimnetic temperatures in fall averaged about 1 degree Celsius for September since 2001 compared to the earlier periods. And Mendota summer temperatures increased about 1 since 1981 compared to earlier. Trout Lake's temperatures since 1981 did not increase, but fall temperatures exhibit a steep trend slope. The same effect observed in Mendota resulted from unusually cool fall temperatures in the early period years, as verified by Mendota's long record. Trout summer's temperatures averaged about 1 degree C, increased and averaged about 1 degree C since 2001 compared to that Dust Bowl period. About minimum temperatures, the maximum recorded temperatures were similar between the two periods. Midsummer hypolimnetic temperatures were highly variable and exhibited a cooling trend slope of more than 1 degree per century in Mendota and Trout Lakes. Strong relations were found between meteorological summer and limnological summer. The thing is dead, but that's okay. Strong relationships were found between previous month's mean air temperatures and Mendota's first of the month water temperatures. But a month's starting water temperature has no influence on next month's starting water temperature. And here I am, having sampled lakes for 50 years of my career. We'll take questions, I guess. So, Paul, do you want to take the mic, or how are we going to do this?
So, I think we're going to try, is everyone good at projecting? We all have our outside voices on? Okay. I'm going to try to do that, and if I need to run the mic back and forth, we can also do that, okay? All right. I saw a hand here. Go ahead.
2 questions for you, Dick. 1, if the long-term trend for Mendota is that the surface temperatures are increasing, your graph showed that at the bottom of the lake, they were decreasing. So one question is, why is that happening? And two, does that imply that the overall average temperature of all the water in that lake is pretty close to almost no change at all?
Well, I wouldn't want to calculate the temperature. The question is related to the temperatures that increased slightly on Mendota's surface waters, mixed zone, and decrease in the hypolimneon. One of the reasons, wind speed will be a big factor. If it is not as windy and we're having a few more warmer earlier periods, warming up and low wind are going to cause that bottom water to, the stratification to set up with colder temperatures. And that's been modeled and is pretty robust. The question now we want to be looking at is on wind speed. We got to get some wind data, if you can trust it. Madison moved its wind anemometer at the airport, and they added in a windshield area where they were not getting good wind data for a whole bunch of years. So we don't have, and then it was on the meteorology building for a while versus the airport. So we don't have a good long record of wind. So, but the other thing, I wouldn't want to say that the average temperature of the water column, because it changes so rapidly in a certain depth zone, and the volume of the hypolimneon is a lot smaller than the volume of the epilimneon. I wouldn't want to make a statement that the whole water column temperature as a whole water mass temperature has changed. I don't know if I could answer that.
Does the eutrophic condition of the lake have an influence on warming? In other words, if you have two containers of water, one is cloudy and eutrophic, one is clear, and you expose them to sunlight, do they warm up differently?
Well, yeah, I mean, water clarity is viewed as a factor. In fact, if you go to a bog lake, with a lot of tannic acids in it, the temperature will all go into the top 1 meter, and it's very cold down below it. So it's thought that water clarity, the Madison lakes haven't changed enough to affect the water clarity readings. Like they haven't been, 10, 12 meters gone down to 2 meters or something. So it hasn't been a factor. They were tested by Madden McGee in her thesis, and we had the water clarity data, and it didn't show any significant relationships.
I think we have time for one more. Any other questions?
Dick, I was surprised when you said there's no oxygen at the bottom of the lake. What does that affect? Is it always that way, and does it have an effect on plant animal?
Well, Lake Mendota, believe it or not, had no oxygen in the bottom back in the early 1900s when Bird and Jude were actually measuring it. So some people thought that oxygen probably had gotten worse, but that's not the case. It's certainly different per lake. Devil's Lake has oxygen, at least in the thermocline, and they can put trout in the lake because there's enough oxygen where the water's cooler. So that's why they're able to do that from a management point of view. The oxygen conditions and anything that's fertile, all that organic matter comes down to the bottom. Once the lake's stratified, it's down at the bottom, and bacteria will consume are munching on the organic matter and consuming the oxygen. So the oxygen has gone out in Mendota usually around the first part of July, sometimes a little earlier, sometimes not. Again, when it stratifies, colder bottom temperatures make the bacteria not as active. So if it's the difference between 8 and 15 degrees Celsius, that would have an effect on how quickly the oxygen would be removed. But these eutrophic lakes normally lose their oxygen pretty much at the start of summer, or in Mendota's case, being real deeper, maybe 1st of July. Trout Lake is not as fertile, much deeper. It doesn't lose its oxygen all the way through the hypolimneon. I'll stand around and I'll be happy to answer questions if you want to ask me afterwards. I enjoy doing it. Thank you.
I could just give him the mic back and probably go for another hour. But thank you so much, Dr. Lathrop, and thank you for staying around just a little bit. If we don't get to your questions, the usual spiel, please email Clean Lakes Alliance. They will find an answer for you somehow, somewhere, and get back to you. Maybe from that
Don't
related-
trust their answers. They answer in Fahrenheit, first of all.
Our next Clean Lakes 101 is going to be Wednesday, September 9th. We're already talking about September, I know. And we're going to get an update on Dane County's Suck the Muck campaign, which is always fun to see how that is going. You want to be there for that. We have more information on upcoming events, all the other fun things going on with Clean Lakes Alliance on the website. Thank you so much for joining us this evening. Please drive safe as you head out to Skyway.